Alright guys, I apologize for not being here yesterday. My son woke up with a fever, so I stayed home with him to take him to the doctor. What did we do yesterday? Did we use it as a homework day? Yeah. Or study hall? Okay. Or that too.
No, we did homework.
We did homework. Yeah. So because I wasn't here yesterday, I reevaluated our schedule, and because I really want to make sure that we're able to fit certain things in timely before Thanksgiving rolls around. I know it's the last day of October, but Thanksgiving is going to be here before you know it. So what I'm thinking is our quiz is still going to be on the 6th, okay, and our test is still going to be on the 11th and 12th, so nothing changed there. But instead of having your pass-fail on the 5th, okay, which is next week, I'm actually moving it to the day before break, which I think would be okay because we have a shortened day that way anyway. We have an early dismissal, so I think having a pass-fail on that day would be better than having just a regular class, because we have those shortened periods. Do you understand where I'm going with that?
Well, we still have this class.
Mm-hmm. We still have all periods.
Oh.
They're just half hour. Okay, at least that's what it was last year, so I'm assuming it's going to be the same thing for this year. Okay, so when I look further into the future, I'm anticipating, I know it's in advance, but our Unit 4 test to be the 25th and the 26th before Thanksgiving break. Now, Unit 4 is not very long, but it can be demanding because there are some interesting topics that we're going to cover in that section. So instead of having one Unit 4 test that covers quite a bit of material, I'm going to break it into 2 parts. That way I think it's a little bit more beneficial for you that you have just a little bit of content on one test and then a little bit of content on another one. Okay, so the first half of Unit 4 test will be before break. Okay, so this is our schedule as of now. Okay, I don't know if I'm going to miss another day. I don't know if we're going to have a freak snow day or whatever, but that's what we have for now. Okay? All right, I believe we had one more example to go over on page 178 where we were talking about kind of the meaning of a derivative, how we can use a derivative to represent particular scenarios in context. So we want to make sure that we can identify the units as well as what a value actually means. So taking a look on this page, it says E of x is the elevation in feet of the Mississippi River when it's x miles from its headwaters. Do you know what that means? Where it starts. Okay, so the Mississippi River starts at Lake Itasca, if you want to say it that way, in Minnesota. Okay, so we're not necessarily calculating a value for these questions. If you read them real quick, they are asking us about particular units or think about this scenario. So can we think about how the elevation is changing? Remember, a derivative is a rate of change. So when it says E prime, we've got to figure out the rate at which the elevation is changing. Can we think about the units? Maybe labeling independent and dependent can help you with that. Independent is usually your x value, and dependent is your y value. So in terms of units, our x is representing miles, and E of x is feet. What would the units for the derivative be? AKA slope. Say it again? Feet per mile. Okay, we have the change in the y over the change in the x. So we need the y unit over the x unit, feet per mile. All right, so now that we know the unit, can we think about the sign of the derivative? Is it positive or negative? So as the water starts at this lake and then flows down the Mississippi River to the Gulf of Mexico, can we think about how the elevation is changing? Maybe that can clue us into what the derivative is. Are we familiar with geology? Yeah.
I'm thinking that the elevation is decreased
Why?
because like gravity, like the water needs to go down.
Water has to use the toll of gravity has to pull the water down to the equator. So you're going to have a higher elevation when you're up north, and then the water is going to flow down as it comes south. So if it's starting up north in Minnesota and it's ending at the Gulf of Mexico, the elevation in Minnesota would have to be higher than the elevation at the Gulf of Mexico where it ends. So if the elevation is decreasing, the sign of the derivative would be negative. Okay, so we have a negative derivative. Okay, so we'll say negative because the elevation decreases from north to south. And we're going to see more of this interpretation as the year goes on, just making sure that we have the correct units and we understand what a value is. And remember, a derivative is a rate of change, so something has to be increasing or decreasing depending on the sign of the derivative. Okay, we'll spend more time with that in Unit 4. All right, in the meantime, we're going to start the next section of 3.5, and we're going to be relating this concept of continuity that we spent a lot of time with in the first unit, and relating it to what's called differentiability, kind of a big word or long word to say. Differentiability just means that the derivative exists. The slope exists. So we're going to explore some different instances here. When does a slope exist? When does a slope not exist? How is it related to continuity? Okay, we're going to kind of bring all these concepts together. So what we're going to do, just as a little exploration here, is graph this particular function, get a picture of it, and then we're going to analyze that picture for certain characteristics. So we'll type in the square root of x squared minus 4. And we'll let it match the window on our paper. We'll go from -5 to +5. So just as a rough shape, it looks like we have a dot at -2 and +2, and we kind of curve upwards from there. Can we get that graph? All right, so based on this picture, can we determine if we are continuous at 2? Continuous generally means you can draw it without lifting up your pencil, aka no hole, no jump, no asymptote. Do we have anything like that going on at 2? No? Okay, so we could say yes. Continuous at x equals 2 because there is no discontinuity. Okay, no hole, no jump, no asymptote. All right, let's check out the next one. Find the value of f prime of 2 to determine if f of x is differentiable there. Okay, does the derivative exist at that spot? Does the slope exist at that spot? So taking a look at our function, can we think about how we want to find the derivative? I know we can do it on our calculator because notice how they want us to find a derivative value, but can we just practice by hand how we could do this? Say it again?
Chain.
Chain. Good. All right, so the derivative will bring down the power of a half from the square root. We'll keep the inside. New power would be -1/2. How do we finish the chain?
multiplied by the derivative of the inside.
Derivative of the inside, which would be 2x. So if we clean it up, the 1/2 times 2 can go away. And a negative power can move to the bottom. Maybe you want to rewrite it as a root. And the x can stay up top. So there's our cleaned up derivative. They want us to plug in 2. So we'll get 2 over the square root of 4 minus 4. 2 over 0, which would be undefined. Okay, so using terminology here, or kind of phrasing, we would say f of x is not differentiable, meaning the derivative doesn't exist. Okay, you could say that as well. Okay, the derivative doesn't exist, but f of x is not differentiable at x equals 2 because the derivative is undefined. Can you think about why the derivative doesn't exist at this spot? What do you think, Anuj?
For the derivative to exist, the limit at that point also has to exist, and I don't think the limit exists at that point.
How did you know the limit has to exist?
Because like the definition of derivative is like that h limit,
Mm-hmm.
so that limit wouldn't exist, so the derivative wouldn't exist.
Because there's no left or right coming in. Okay, that you can definitely look at it that way. What's our definition of a derivative? Derivative is the slope of a tangent line, and tangent line only touches once. So if you were to draw a tangent line that only touches this spot, how would you draw it? You could draw it any way you want. You can go like this, you can go like that. Notice how I'm only touching at that spot, right? You could go this way, you could go that way. So since it's basically an endpoint, the tangent line could look, or could take any shape or any direction. So if the definition of a derivative is the slope of the tangent line, and you have infinitely many tangent lines as possibilities, there's no way you could determine what the slope would be. Okay, because there's no actual one tangent line, there's no actual one slope. So we can say in this case that it's not differentiable specifically because x equals 2 is an endpoint. Okay, we're going to take that into consideration as we go through some other examples. So from here on out, we now know that a derivative does not exist at an endpoint. Okay, because the limit doesn't exist, you don't have that left or right side, we don't have a specific tangent line to find the slope value, however you want to look at it. Okay, so endpoints are kind of clues for not having a derivative, not having a slope. All right, let's check out another example. So we'll type this function in on our graph just to get a picture. X to the 1/3 plus 2. Interesting, yeah. So it looks like we have a y-intercept of 2. Makes sense because that's the constant on the end of the equation. And we kind of curve up. All right, so there's our rough shape. So our special location that we're interested in now is the x location of 0. Are we continuous at 0? No hole, no jump, no asymptote, right? Okay, so yes, continuous at x equals 0 because there is no discontinuity. This might be a good time to bring in our definition of continuity from Unit 1. I know it's been a while. Do you remember what we had to check in order to see if we were continuous? My holy trinity of continuity, yeah.
No, one of them is the overall limit.
So from the left and the right, the limit must exist. Yeah.
It has to be a value.
There has to be a point. Yep.
And that's
And they have to match. Okay, so notice at 0, you do have a closed circle. Okay, so the point exists. From the left and the right would meet, so the limit exists. And the left and the right would specifically meet at the point. So if we wanted to use our definition, we could say the point at 0 equals the limit as we approach 0. Okay, our holy trinity of continuity. Let's go ahead and check out the derivative. So we could use our power rule because we have x's to powers. So 1/3 x to the negative 2/3. If we clean it up, 1/3x to the 2/3. And if you want to change it to a root, you can, because you have that fractional power. But either way, we want to plug in 0 and see what we get. So 1/0. Looks like we have another undefined derivative. Okay, so using terminology, mathematical words here, f of x is not differentiable. Okay, the derivative does not exist at x equals 0 because f prime of 0 is undefined. Now this is going to bring up another interesting spot because notice how 0 is not an endpoint like we had in the previous example. So something else must be going on in this little section to cause the derivative to be undefined. Yeah?
You can't draw a tangent line without touching more than 2 places. Like it would touch more than one.
Okay, so visually I can see that. If you were to draw it, if you tried to draw one though, what would it look like?
Vertical.
Vertical. Okay, so it would be a vertical tangent line. So I can see how you think it's going to touch twice. This is another interesting spot that we're going to talk about in the next unit called a point of inflection. Maybe you've heard of that before, maybe you haven't. But that's basically where the curvature changes. Notice how this one is curving up, whereas this one's curving down. So when you're at a point of inflection, the tangent line does look like it would touch twice, but that's because the curve is changing. But if you were to draw a tangent line, notice how it would be vertical. What's the slope of a vertical line? Undefined, okay? The slope of a tangent line is undefined. So it looks like we have another interesting graphical characteristic to look for. Okay, we can find, let's see, x equals 0 has a vertical tangent. So not only can we take a look at endpoints and know the derivative doesn't exist there, but if we can find those vertical tangent spots, we know the derivative doesn't exist there either. Okay, we're looking for these interesting places where the derivative does not exist. Let's try the next one. Okay, we're going to graph it just to get a picture. I think the only difference with this one is the power is 2/3. Yeah. So y-intercept at 2. I don't know about you, but that kind of looks like the birds I used to draw when I was in elementary school. You know what I mean? All right. Are we continuous at 0? Do we have a point? Do we have a limit? Do they match? Yep. Yes. Continuous at x equals 0 because the point equals the limit. You could also say there's no discontinuities there. Okay, same thing. Let's try the derivative. So f prime of x, using our power rule, we'll have 2/3 x to the negative 1/3. Cleaning it up, 2/3 3x to the 1/3. And we want to check 0 again. 2 over 0, undefined. So f of x is not differentiable, okay, aka the derivative does not exist at x equals 0 because f prime of 0 is undefined. So some interesting characteristic must be happening at this location of 0. It's not an endpoint, okay, and if we were to draw a tangent line, it wouldn't be vertical. So something else must be going on here. Why do you think this spot doesn't have a slope? If you try to draw a tangent line, what would it look like?
Horizontal.
Maybe.
Well, could be,
It could be horizontal.
could be vertical.
I could do that, right? Just touching at that spot. If I were to draw a little tangent line. You see how there's multiple ways to just touch that one spot? Okay?
That would be vertical.
You could do vertical, yeah, right? Point is you have more than one, right? Point is you have more than one, okay? So this is kind of similar to the reasoning for the endpoint, where if you have multiple tangent lines, you have multiple slopes. So how do you know exactly what the derivative is? What is that one slope value? Now this is what's called a cusp. Maybe you'll see that word on in some books or some worksheets, okay? But a cusp is basically a sharp point, like a drastic change in the graph. So this is an example. An absolute value would be another example because you have that sharp point on the bottom. So we can say x equals 0 is a cusp or sharp point, whatever terminology you want to use. Okay, so we have 3 characteristics that we want to be on the lookout for in order to see or determine where a derivative or slope doesn't exist. So we got to check out endpoints, we got to check out the sharp points, and then those vertical tangents, okay, where the tangent line would be going up and down. So we're going to kind of rephrase that or paraphrase that on the next page. So based on what we've seen, can we think about, does continuity imply that the derivative exists? Or does the fact that the derivative exists imply continuity? Can we think about the connection here? Do you have to be continuous in order to have a slope? Or do you have to have a slope in order to be continuous? It's kind of like that thing, are all rectangles squares or are all squares rectangles? Kind of got to wrap your mind around it. What do you think, Anish?
I think it's the second one.
Why?
Because the first one isn't true. I have no idea.
Does continuity imply... Okay, so let's take a look. In the 3 examples we did, didn't we say all 3 of them were continuous, right? But the derivative did not exist. So continuous does not imply differentiability. Just because you're continuous, no hole, no jump, no asymptote, does not mean that the slope exists or the rate exists, if you want to think about it that way. The other way around is true, because if you have a slope at a particular point, doesn't that mean that you have to have that graph there in the first place? Meaning you don't have a hole, you don't have a jump, you don't have an asymptote. Okay, so we're going to say differentiability, the fact that the derivative exists, implies continuity. All right, so in paraphrasing words, we can say the slope at a point exists. That means that the point must exist. And the limit, okay, but the point itself is a condition for continuity. So kind of like continuity, we had those three things that we had to check, the Holy Trinity. We have two things to check in order for a function to have a derivative at a particular spot, okay, have a slope. So in order for us to have a slope, notice how continuity is a condition. Okay, you have to have a point there in order for you to be able to draw a tangent line. So f of x must be continuous at some spot. Okay, we'll say x equals a. The other thing we have to check is kind of leading into what Anush said earlier about limits, is not only must the left and the right side at a point be meeting, but they have to be connecting smoothly. Okay? We can't have any sharp point here because we know that the derivative would not exist. So the left and the right is a condition for continuity, but it's also a connection for, or a stipulation for differentiability. They have to be connected smoothly, okay? Nothing drastic like this point. And in order for the left and the right to be connected smoothly, the slopes from the left and the right would have to be the same. Because if you have a slope of, let's see, we'll go this way because it's backwards for you. If you have a slope of -1, and then a slope of +1 right after that, are those connected smoothly? No, because you have that sharp point at the bottom, right? So in order for the derivative to exist, the slope from the left and the slope from the right must be the same. Those are connected smoothly. The moment I change the slope, notice how I get that sharp point. So it's no longer differentiable there, because a sharp point is one of the things we have to look out for. So in terms of limits, we got to make sure the limit from the left of the derivative is equal to the limit from the right for the derivative. Okay, the slopes must be matching. This is us basically checking to see if f of x is smoothly connected. All right, so to just reiterate this idea of being smoothly connected, that means no endpoint, no sharp point, and no vertical slope. Okay. So just like there's three things for continuity, whole jump, asymptote, there's three things for differentiability: endpoint, sharp point, vertical slope. The rule of three shows up a lot. Okay. So what I wanted to spend the rest of today practicing, based off these graphs, where can we determine a location where the derivative would not exist? Okay, it has no slope at that particular spot. So it has to be one of these three conditions then. There must be an endpoint, there must be a sharp point, there must be a vertical slope, because those are the only three locations where a derivative would not exist. So can we check out the first one and try to label anything? What do you think, Christian?
I would say x equals 0.
Okay.
There is not a derivative. Because
Why?
it is discontinuous.
Discontinuous. Okay, so notice how continuity was one of our conditions. You need to have a point or a connection there in order for a slope to exist. But that's not the only condition, because if the points are connected, okay, they have to be smoothly connected. Okay, if they're not, you're going to have that sharp point. Okay, so we'll say x equals 0 because it's discontinuous. Do you see another one, Christian?
I do.
Where?
X equals -4 because it's a sharp point.
Sharp point. Okay, so x equals -4, sharp point. Okay, derivative does not exist at that x equals -4 location. Any other ones? We gotta look for discontinuous locations, but also these three. Good, Addison? It's an endpoint. You See another one, Anuj?
Actually, we positive 4 because there's no point.
Okay, we'll assume that's 4 there. So there's no point there. So they would be discontinuous. Okay. Any other ones? There's one more and it's tricky.
The end point on 0. Like the bottom.
Oh, like this one? Well, this location of 0 is including both of these. And notice how that's a jump. So that would just be discontinuous.
X equals like 2 1/3.
2 1/3? Why? What's going on right here?
Vertical tangent.
That's a vertical tangent. If you try to draw a tangent line, okay, we kind of have that change in curvature again. We'd have that vertical tangent. That's always the hardest one to find. So we'll say maybe x equals 2.5 just as an estimate. Okay, vertical slope or vertical tangent. So the derivative would exist at every other point on this graph. Okay, we would be able to draw a tangent line and estimate its slope, but it's not existing at these particular locations for these reasons. Okay, so there's no rate of change, there's no slope at those spots. Can we try the next one to the right? Go ahead, Christian.
X equals 3 because it's a sharp point.
Sharp point. Okay, so x equals 3. Sharp point. Or cusp. Yeah.
X equals 0. Discontinuous.
Discontinuous. Looks like we have an asymptote there. Okay. Is that it? You see one? Yeah.
X equals 1 because vertical asymptote. Or vertical.
Vertical tangent. I don't know if it's vertical. If you plot the point at 1 and draw the slope.
Somewhere around there.
So you're probably thinking like right there, where it'd be vertical, like when you could start to go down. You don't know? Okay. Well, I'm just saying it wouldn't be 1, because if you plot the point and then draw the line, that's not vertical. I think what you might be looking at is this spot here, and that's getting closer and closer to 0, that we already said wouldn't work, because it's discontinuous. I think those are the only two, though, because we don't have any endpoints, right? We have the arrows. Okay. What about the one below it? Go, Christian.
X equals -1 because there's a jump or something like that.
Oh, you're looking. Oh, did I say the one below it? Okay, sorry. -1. Okay. So x equals -1. If there's a jump, it's discontinuous. Any other spots? Keep going, Christian. Yeah.
It looks like X equals 2. There's a sharp point.
Sharp point. All right. Derivative or slope does not exist there. Go to Noosh.
X equals what is it, -4. It's a-
1, 2. Okay, we'll say -4, and it's an endpoint. All right. Slope does not exist there. Yeah,
Looks like X equals 4 is another endpoint.
is another endpoint. All right, so the derivative exists at every other spot except those ones. What about our last one? Go to Noosh.
X equals -1 is a vertical tangent.
Vertical tangent. Vertical tangent, vertical slope. Good, Christian?
Like a little bit before X equals 4, there's a sharp point.
Okay. We'll just round it to 4, but it looks like it'd be a little bit before. Okay, sharp point. Austin, did you have another one, or were you going to say that one?
Yeah, 5 is the endpoint.
5's an endpoint. All right, so the derivative, aka slope, does not exist at those spots. I think we're good. Does that seem okay? Can we identify those locations? Okay, so you got to look out for holes, jumps, and asymptotes because that's where you're discontinuous. But then you also have to check out endpoints, sharp points, and vertical slopes because a derivative wouldn't exist there either. Okay, so a total of 6 things we got to check for to see if the derivative would not exist. All right, we'll stop there for today. Tomorrow we'll get into more of an algebraic approach on how we can determine if the derivative exists at a spot. But for today, I'm happy that we got through the graphing examples.